Hello and welcome to a digital lecture for Salt Lake Community College. This lecture will be the third to cover section 4.2 for Intro to Statistics, considering one sample means with the t-distribution. And we'll also briefly discuss creating a special type of graph in GeoGebra, so I recommend to have a tab open for GeoGebra to practice. The plot we will discuss is what is known as a normal probability plot, which is another method for checking the assumption of normality, where the closer the points are to a perfect straight line, the more confident we can be that the data follows the normal model. This can sometimes be easier than looking at a curve and judging its normality based on how smooth and symmetric the curve is. We can create these in GeoGebra as shown below. The instructions state that in the GeoGebra spreadsheet, enter the data, click on the histogram icon in the top left corner, and select one variable analysis. In the histogram window, select the normal quantile plot from the drop-down menu. I will demonstrate this. In my plot here, I already have a random set of data that I made up, 14 points here, and I already have it selected. Currently, when I click on this histogram picture, it will give me this image. However, if I would like to change this instead and see what this would look like as a normal probability plot, I will go to this drop-down menu for histogram, and I will see normal quantile plot at the bottom. That will change my image instead into a normal probability plot, analyzing how well this data fits a straight line. Back to the notes, we then have finding a t-confidence interval for the mean. Since we are now working with the t-distribution, we should be able to apply some of our methods from previous chapters, such as a confidence interval. There are not many differences, but you should pay careful attention to what defines the margin of error here. We have that based on a sample of n independent and approximately normal observations, a confidence interval for the population mean is x bar plus or minus t star with a subscript of df times se. We know that x bar is the sample mean. T star with a subscript of df is a little bit new to us. This corresponds to the confidence level and the degrees of freedom. And se we know as the standard error as estimated by the sample. That t star with the subscript of df may be new to us, but it sits in the same place as something that is familiar to us, which is the requisite z-score. Because of its similarity to a z-score, we will thusly call this a t-score. To help us remember to use the t-distribution, we use a capital T to represent the test statistic, and we often call this a t-score. The z-score and t-score are computed in almost the same way, which should not be surprising since they are both models that are either normal or very similar to normal, and are conceptually identical. Each represents how many standard errors the observed value is from the null value. The difference is that the standard error in the t-score is computed using a sample standard deviation of little s, while a z-score is computed using the population standard deviation, sigma. When in the second stage of the statistical process, designing a study and gathering the information, we often want to make sure we have a big enough sample size before we gather the information to save time and resources. The sample size calculation formula for estimating a single mean, quantitative data, can be written as little n is greater than or equal to z star times little s divided by me squared. Z star, remember, is the requisite z-score, little s is the sample standard deviation, and me is the margin of error. This formula is found by taking the confidence interval formula before and deconstructing it. Recall that when doing this in such calculations, we always round up for the sample size. This is very important, as if we find a statement such as n is greater than or equal to 192.3, then if we were to choose a sample size of 192, we would find that this statement is invalid because 192 is not strictly greater than or equal to 192.3. This is not valid. Therefore, we would need to round up this decimal value to the next integer of 193. This would be a justified sample size to select. If you have any further questions, be sure to review the example videos or ask your instructor.